because, well, my talk is to some extent related to that. In fact, an intermediate talk, which is missing, is even more related. Of course, that's not by chance. I mean, they were put together precisely for that reason. Well, this is joint work with ORIZON FERREIRA and SANDOR NÉMETH. ORIZON FERREIRA from Federal University of Goiás in Goiânia in Brazil, and SANDOR NÉMETH from University of Birmingham. They have been studying precisely Hadamard manifolds, which are much simpler than Hadamard spaces, and several years ago they precisely also studied the proximal point method in Hadamard manifolds. And well, the point is the following. As Miroslav has just rightly pointed out, when you have a manifold with negative curvature, projections are non-expansive. And this is very good, because when projections are non-expansive, the convergence analysis, for instance, for the proximal point method as developed by Rockefeller in the 70s, carries over, and in manifolds it's easier than in spaces, but basically you have all the stuff. Now I'm going to speak about the sphere. The sphere, as you know, is a manifold with positive curvature. When you have positive curvature, unfortunately, projections are expansive. For instance, if you take 2 points, let's say, for instance, one in Ireland and one in England, and you project them over the equator, they become farther separated than they were there in the northern hemisphere. Since that happens, well, the whole convergence analysis, let's say, things become really bad. So not much can be said in terms of algorithms and so on manifolds with positive curvature. So we decided to start with the sphere, because the sphere is the easiest one, and even there our results are very partial. That we knew in advance, because so we don't have yet too many algorithmical results. We will practically do the very, very basic convex analysis in the sphere. We will introduce the definition, see some elementary properties, some characterization. We hope, nevertheless, to have some future algorithmical results, perhaps with a completely different approach than the approach for convex algorithms in Euclidean or Hilbert spaces. Okay, so, well, this paper will be shortly published in TOP. TOP is the Spanish optimization journal. And, well, so this is the summary of the talk. And I will, as I tell you, deal with very, very elementary. So this is a very introductory talk. We will just mainly introduce the right language to discuss these things: convex sets in the sphere, convex function and convex optimization on the sphere, and variational problems and monotone fields on the sphere. The idea is that the sphere, since it has a very simple algebraic structure, it will be easier to deal with it than with a general positive curvature manifold, where things become much more complicated. So, well, this is just what I have already said. Now, there are many optimization problems which are naturally posed on the sphere, and the idea is that we can exploit the underlying algebraic structure. And, well, and there are many, many applications, like numerical multilinear algebra, solid mechanics, signal processing, computational anatomy, quantum mechanics, and others. And, well, so we'll move to the problem. The sphere is just the unit sphere in Rn, I mean in Rn plus 1. And we have just a function defined on Rn, and on Rn plus 1, sorry, and I want to minimize it on a subset of the sphere. This is my problem. Minimizing a convex function. No, convex not, a function, in principle, on a subset of the unit sphere. For instance, if I just take see the whole sphere and I take quadratic form, this becomes a minimum eigenvalue problem, that is finding the spectral norm of the matrix minus Q, if Q is the matrix of the quadratic. And this problem includes this quadratic one as particular cases, problems of deciding the non-negativity of a homogeneous multivariate polynomial over the sphere, as well as the biquadratic optimization problem over unit spheres, and others. With the quadratic objectives, it includes the transformation subproblem of many nonlinear programming algorithms. This is interesting. Just in general, in many transformation methods, you at some point have to solve as a subproblem a quadratic problem with quadratic objective over the sphere. And then I will mention a third case, which is the facility location problem. I have m points on the sphere, and I want to minimize a weighted function, a weighted sum of the distances to these points. And d is the distance on the surface of the sphere. We will be more precise about this. So the spherical facility location problem is defined precisely like that. You want to find a point which minimizes the weighted sum of the distances to m given points in the sphere, which also has a lot of applications. In chemistry also, molecular deployment or unfolding, that is molecular unfolding. Yeah. And well, several algorithms for solving these spherical facility location problems are subgradient type algorithms for optimization problems, though, there is a whole literature about the spherical facility location problem with specific algorithms, mainly put together by people who are not mathematicians, who are just in the applications, and they are basically a subgradient problem, but they do not see them as that. They develop. Okay. Now I will move to the specifics of the talk. And the first thing I will do is to define the intrinsic distance function from point Q, which is just the function d sub Q defined at the point P, just like the arc cosine of PQ, because that is just the length of the geodesic, which in this case I have this very nice. This is the type of thing that we will exploit, that if I am with a sphere, everything has very nice formulae, which wouldn't be the case in a general positive curvature manifold, Riemannian manifold. And it satisfies all the nice properties that you want, that you expect. Of course, the distance goes into 0 and P. If the distance is 0, it's because P is Q. And if the distance is P, so the angle is half the, two right angles, then P is just the antipodal point of Q on the sphere. And, well, the point is that the intrinsic distance is twice differentiable, excepting at the point and at the antipodal point. And we have very explicit formulae for the gradient and the Hessian. That helps. And, of course, you cannot take P equal Q or P equal minus Q, because, as you see, those square roots will explode. And it is easy to compute the spectral decomposition of the Hessian, and there is this lemma, and the conclusion of the lemma basically is that there are only two eigenvalues of the Hessian, which is 0, and the other, which is PQ over the square root of 1 minus PQ squared, which have multiplicative, have multiplicity 1 and n minus 1. So it follows that if I take 2 points which form an acute angle, the Hessian is positive semi-definite, and if they form an obtuse angle, the Hessian is negative semi-definite. All this is very easy to check, but these properties turn out to be quite useful. And now we present a similar result for the Hessian of the square of the intrinsic distance. As you saw before, when I took the distance is not differentiable at the same point and the other point. It will be like the differentiability of the square of the norm at 0. Here I mean the norm at 0, but the square is always differentiable, so let's go with the square. And then I have a formula, which is this one. Oops. I always have trouble with this thing. Sorry. Oops. Okay. Oops. Intrinsic distance. Oh. Sorry. Okay. Here I am. Let's try to no the next one. Okay, here I have the formula for the, I mean, the similar result for the Hessian of the square of the intrinsic distance. And again, I have only two eigenvalues, multiplicative 1 and n minus 1. And again, if P and Q form an acute angle, the Hessian of the square of the distance is positive definite. If the form of obtuse angle, not anymore, because the idea is that if you have a negative definite matrix, the square is not negative definite, but it's not positive definite either. So let's say nothing can be said in general. Okay, so we continue. And now we move to convex sets in the sphere. And well, they are very much related to pointed convex cone in Euclidean space. Well, a set is said to be spherically convex, exactly as with the definition of Miroslav, meaning that for any pair of points, the minimal geodesic segment which join both points is contained in the set. And for instance, the intersection of the sphere with the non-negative orthant of Rn plus 1 is convex. Now, the relation of convex sets in the spheres and convex cones in Rn plus 1. If I consider the cone spanned by a subset of the sphere, meaning the cone formed by all the directions between all the vectors between 0 and points in the sphere and the half-line generated by them, then it tends to be that, well, and recall that the convex cone is pointed if it doesn't contain straight lines. So the proposition is that a set C is spherically convex if and only if the cone spanned by it is convex and pointed. Okay. Now I define the spherical polar set of a spherically convex set, which is defined as, well, the set of points which are at distance bigger than pi over 2 of the given point. And here you have, this was a question that Regina made before, whether you have some sort of duality, and the answer basically was, as Miroslav said, in Haldeman spaces not. In manifolds, yes, and it goes like this in the sphere. And you could do this in other manifolds, because this is like the dual, this will lead to a dual problem. Okay, and so, well, the polar set is precisely the points which make an obtuse angle with all the points in the given set. This is the polar. Now, if I look at the Kc minus is the polar cone of the cone Kc in the usual sense, then it turns out to be that the cone of the polar set, well, no, that is the definition. Just case sub, well, it's just the cone spanned by the polar set, but then the proposition said that if I have a set which is spherically convex with non-empty intrinsic interior, then the cone spanned by the polar set is the polar cone of the cone spanned by the set, which is pointed. Additionally, the polar set is spherically convex. The polar set is always closed, and the polar of the polar is the closure of the original set. So everything works like as one would expect. Now, the open hemisphere with the pole is just the point which are make an angle less than strictly acute with the, strictly obtuse, strictly less than obtuse, strictly acute with a given point. So it's the open hemisphere, consider that the point given is like a pole, and this is a convex set, which is not the case if I consider the closed hemisphere, because in the closed hemisphere I have also a geodesic which goes through the other hemisphere. So the closed hemisphere is not convex, the open is. So precisely, if I have a closed spherically convex set, there is a point in the sphere such that C is contained in the convex hemisphere related to that point. So every convex subset of the sphere is contained in an open hemisphere. Something bigger, which does not fit, not bigger than the hemisphere, but which does not fit a hemisphere, cannot be convex, because then you have always the geodesic will go to the other side. Okay. Well, as before, I can define the projection onto a spherically convex set. The set of minimizers, this is not, I'm not saying that it's unique, but it's a set of minimizers. It's a point to set mapping, that's the parts of C, which minimize the distance. That's okay. As I tell you, it is expanding. Instead of being non-expansive, it is expansive, which is awful, but okay. And the minimal value of the distance is called the distance to a point, denoted like this. I mean the minimum distance from P to a point in C, the distance to C. So we can say that the polar set is the set of points at distance bigger than pi over 2. The projection mapping is monotone. This is interesting. It's monotone, it's spherically monotone, in the sense that we have P bar minus Q bar, a scalar product with V minus Q is non-negative for all P bar, which is a projection of P over C, and all Q bar, which is a projection of Q over C. We have monotonicity. Okay. So, properties of spherical projections. Well, here you have, I have a closed spherically convex set. I take a point in Sn in the sphere, another point in C, and then and the 2 points make an acute angle. So in this case, it is equivalent to say that P bar is a projection of P over C. This inequality there, where I is the identity and P bar transpose just the matrix, or to say that that vector P minus P bar belongs to the cone spanned by the polar set. And when we have that fact that the 2 points make an acute angle, the projection is a singleton. We continue with additional properties. Well, this is property of the projection, and this one is that if the C is contained in a hemisphere, the projection onto C is continuous. Not if it is not. For instance, the projection, as I was saying, like onto the equator, is not because it fails at the pole. I mean, the pole could be projected into any point of the equator. I mean, it's not point to point, let's say. But projections onto convex subsets are. I mean, if you take a hemisphere, the projection of the other pole, the other pole onto a hemisphere would not be point to point, it would be any point in the equator. Well, now convex functions in the sphere. Well, a function is said to be spherically convex if the composition of the function with any geodesic is convex in the usual sense, as a function of the interval 0, 1. to R. So, and it turns out to be that the function is spherically convex if and only if its epigraph on the sphere is convex in the sense that we gave to convexity in the sphere. And the sublevel sets are spherically convex of a convex function. And one interesting point is the following observation. If I want a function defined on the whole sphere, and I want it to be convex, the only chance for it is to be a constant function. There are not convex functions defined on the whole sphere. The convex functions which are meaningful are those whose domain are convex subsets, and they have to be contained in a hemisphere. Okay. So now I have the characterization, the usual gradient inequality for spherically convex functions, which says that f of q greater than or equal to f p times the gradient of f at p times the inverse of the exponential mapping from p to q. And this is equivalent, if I want to write in terms of, let's say, that inequality, f of q greater than or equal f of p plus, and here you have the usual gradient of the function thought as a function defined on Rn. This is just the usual gradient. And all these things are what come just from this, because this is the spherical gradient. Okay. Another property is that, well, now the other equivalence. We know that when you have a convex function, you have the gradient inequality, and also you have, like the other characterization, which says basically that the gradient is monotone. Well, now this second inequality is this one. This, in terms of this null of f is the gradient vector field on the sphere. But if you want to write in terms of the gradient as a function on Rn, it has this larger expression, but it says basically the same thing, and this is equivalent to that thing, gradient of f at x minus gradient of f at y, scalar product with x minus y, greater than or equal to 0. So this is it. Okay. It follows that for all minimal geodesic segments, the composition is convex if and only if we have this formula. This is the geodesic, this is the directional. Well, now Hessians. Again, suppose now the function is twice differentiable, so f is spherically convex if and only if the Hessian satisfies this. This is the tangent space to the point P, and this is the equivalent formulation. This is the Hessian on the sphere, which is a field, and this is the Hessian, the usual Hessian and the usual gradient. So these are the formulas. And well, for all with any of these things, you can prove that if you have a spherically convex set, the distance to this set is a convex function. This was also in the case of Hadamard spaces. And now, convex optimization, a differentiable function, and you want to minimize the function defined on a subset of the sphere on a feasible set which is also a convex set. So, now C in principle, well, but for the proposition it has to be convex. So, the first order conditions are given like this, so the necessary conditions. If a point solves the problem, then we have this first order condition, which is similar to the first order condition in Euclidean space. And when the function is also convex, the first order conditions, of course, are necessary and sufficient. And here I don't need any qualification. And now, with non-empty interior, convex set with non-empty interior, I define the normal cone in the usual way to define them, in the natural way to define it. it lives in the tangent space. And, well, here I take the tangent cone to the intersection of the sphere with the positive orthant, and they are just the vectors which are in the negative orthant. And now I consider the variational problem, which given a vector field X and a convex subset C, I want to find the point P which is feasible and such that the field 0 belongs to the field plus the normal cone, which is, can be written equivalently in these two other forms. And okay, here there is, that would be a C minus, there is an error. Well, and of course, when P belongs to the intrinsic interior, the problem is just to find the 0 of the same as in the Euclidean case. And when C is the intersection of the sphere with the positive orthant, we get this. P has to be positive, the vector field has to be all components positive, and the scalar product has to be 0. So this is the so-called spheric complementary problem. And, well, properties. Then we know that a point is a solution of the, I cannot, a point is a solution of a variation inequality if and only if I take the point, take minus r times the field, take the exponential, and then projection to C, I get again C. This is equivalent of the fact that if you take, in the Euclidean case, you take a point, you move with the operator, and projection to C, you have to recover the same point if it is a solution. And this is for all r positive and such that we have now a constraint on the field, which is this r times the value of the field has to be less than P. Okay, continue. Now we have an existing result, and it is that if the field is continuous and C is closed and non-empty, no, sorry, if the field is continuous and C is closed, then there are solutions, and the solution set is closed. Here, the compactness is guaranteed because they are closed subsets of the sphere. So this is. Now I have variational problems, and well, if a point local minimizers solve the variational problem whose field is the gradient of f, and if f is spherically convex, then a point which solves that variational problem with the gradient is precisely a point which is a global minimizer of f and reciprocally. Okay. Well, this is a corollary which relates to another characterization of the projection, which I will just... and now monotonicity. I say that this is the final part. I say that field is monotone if spherically monotone if you have xp times q plus s of q times p less than or equal to 0 for all pq. This is a little bit different, but it turns out to be exactly what is needed. And for example, if you take an skew-symmetric n plus 1 matrix, then if you take just the function takes p to a of p, this vector field is monotone. Well, then you prove that a function is spherically convex if and only if the gradient, its gradient, differential function, is spherically monotone. Well, and this, we stop here. We have some more properties. As I tell, all this is rather elementary, but it allows us to get quite a few tools to deal specifically with this kind of problem. So these are several works of, the second one is already published, and that dealt only with the properties of the projections, some of which I have summarized here. And there is this paper about subgradient algorithms on Riemannian manifolds with Ferreira and Oliveira, and that in Jota. And let's say, as I was telling you, most of the references up to here, there are a lot, are for manifolds with negative curvature. The references that I am quoting here are relatively few. There are some more, I mean, just picked up the most relevant, are those which apply, which give results either for any general Riemannian manifolds or for Riemannian, specifically for Riemannian manifolds with positive curvature. And okay, this is so. This is all. Thank you very much. Questions?